So with this lecture 2, we are going to formally start the course proceedings in our Fluid Mechanics 2 course. And this lecture, as you can see, is titled Local Deformation and Rotation Rates. So the learning objectives of the second lecture will be that we will be developing a conceptual idea or framework of local deformation and rotation rates. What do we understand by these terms in a medium like a fluid, continuum medium like a fluid, and then the other two objectives of material line kinematics in 2 dimensions. Of course, 2 dimensions is just to make you understand in a very simple manner, so we restrict our attention to material line kinematics in 2D. And the third objective is instantaneous strain rate and rotation rates of infinitesimal material lines. So how can we express them mathematically? The two quantities, the instantaneous strain rate and instantaneous rotation rate of a very tiny small infinitesimal material line in a moving fluid. So that would be the main development when we'll end this lecture, the expressions that you will get for the local instantaneous strain rates and rotation rates of infinitesimal material lines. Right, so we move on to the conceptual framework or visualizing local deformation and rotation rates. So that we do through kinematics of material lines. So naturally the question arises, what is a material line? It is also known by the name of timeline. Both terms you will find in literature on fluid mechanics. So let's try to understand what is a material or a timeline. You have already heard these terms, streamlines, path lines, streak lines. So this may be a new term, but let me tell you, it's actually much simpler than the other ones. So to put it simply, I've written here in quotes, an arbitrary chosen set of fluid particles lying on a curve drawn in the flow domain at a given instant. So what you have to simply do to start with a material line or a timeline, or to create a material line or a timeline in a fluid at a certain instant. So this is important. It's an instantaneous construct, material line or timeline, but with time then the same set of material points or fluid particles move in the fluid. So as you can see, there is a diagram beneath the definition. So it shows that I can construct them either as an open line, so that S-shaped line that I have shown on the left, and I can also construct a closed curve. Okay, so both are material or timelines. These are just curves. You can imagine you draw a curve at a given instant in the flow domain. So the curve will contain practically infinite number of fluid particles over a well-defined shape or the curve that you have drawn. Okay, so this shape in itself is basically identifying the set of particles, which is of course uncountable set because it will contain infinite particles, but it does define a specific set of fluid particles which lie at a given time instant on the curve that you have drawn in the flow domain. So that is the idea. So you can have open as well as closed timelines. Now the next question is, once we have created a timeline at a certain time instant, what happens to this material line as time passes by? So with the passage of time, what happens to the material line? So the figure at the bottom is just a qualitative kind of a sketch to give you an idea of how a timeline can actually evolve in a moving fluid. So at three different time instants, T1, T2 and T3, I have shown the same material line. Same in the sense that I am tracking each and every particle on the material line at T1, and so with the passage of time all these particles now are lying on a curve, dashed curve, which is shown at T2, and then subsequently at T3 on the dashed curve shown at T3. And I have specifically shown, let's say, two very close points A and B, which are on our timeline, which we have drawn at T1. Then as time passes by and timeline evolves, if you just focus on these 2 points A, B, you will notice that the distances between them, A, B, A dash, B dash, A double dash, B double dash, the distances seem to be changing. And as per the figure, you can see that actually the distances are increasing. But it could very well have been contraction also going on. So this is just as figure which explains that the distances can change between two neighboring sort of fluid particles on a timeline as it moves. And not only these distances are changing, which gives a hint of what you call as local strain rate. Okay, so this is how what is meant by a strain rate, that if you are on a material line, then two neighboring points, their distances will change, and this rate of change will be, later on we will show you how we can calculate. This will be the conceptual framework of local deformation rate. Now obviously this is the longitudinal strain, or this is the strain which is directly seen as a change in length between two fluid particles on a material line. Simultaneously, you will be noticing that apart from longitudinal stretching which is going on, there is also some amount of rotation going on. So AB and A dash, B dash and A double dash, B double dash, they seem to be changing their orientation. These material lines, you can say, or rather portions, small portions of the material lines, they seem to be locally changing their slopes or their orientations. So rotation is also clearly a possibility when material lines evolve in time. And of course the material lines are moving. So in this case, if it goes from T1 to T2 and from T2 to T3, we can say that the material line is translating towards the right from left. So you have three effects, which is written on my right. The text written on my right clearly says that material line segment AB is undergoing the following kinematic effects. What are these? Number 1, translation. Number 2, rotation. And number 3, longitudinal stretching, which we call as straining. Of course, it could be contraction also. So these, you must remember these things very clearly, that these are the three possibilities for local possibilities when you are talking of any two neighboring particles on a timeline. Now all this that we are seeing here, you can imagine that it is actually applicable to a full blown three-dimensional flow field. Okay, I'm not right at this moment, when we are setting the stage for local deformation and rotation rates, we are not restricting our thinking to simply two-dimensional flow fields. So timelines, the picture that we have shown here, they could very well exist in a three-dimensional flow field. And all these kinematic effects that we have talked about, translation, rotation, stretching, it could well be going on in a three-dimensional material line. Okay. No need to worry at this stage. When we will develop some expressions, we'll begin with a very simple scenario of two-dimensional kinematics. So there you don't have to straight away go into a more complex three-dimensional world, but the basic ideas are very general. That is what I am trying to stress here. Now, there's one kind of strain which we all know, apart from longitudinal strains. We know that there is something known as a shear strain, and I have not talked about it as yet. So, where is my friend shear strain hiding in this figure? Okay, let us try to see. We can see translation, we can see rotation, the line, the infinitesimal material line AB changing into A, but we are not able to directly see the shear strain. We can see the three things that we have mentioned, but where is the shear strain? So, in order to visualize the shear strain rate, we need to remember that shear strain rate is only a concept which is applicable to two material lines at a given instant, not a single material line. So, the figure that I had shown, evolving material line, since it had only one material line, I could not see or visualize the shear strain. For that, I need to consider, let's say, two material lines, as I have shown in the figure below, 1 and 2. So, now once we have at a given instant two material lines, and deliberately I have chosen them as intersecting, let's say at point A, then we can now consider two neighboring fluid particles neighboring to A, one lying on material line 1 and the other lying on material line 2, say C and B. So now, with the passage of time, it is expected that while point A, fluid particles A, B, C all will translate, there's a very good chance that the angle between AC and AB would also change. Now, in the enlarged view, I have shown that what is the necessary condition that the angle between AB and AC would change. So, it's very easy to say that if the rotation rates, instantaneous rotation rates of AB shown as omega AB and for AC shown as omega AC, if the instantaneous rotation rates happen to be different, okay. So, if they are different, not equal, then we expect that there would be some angular or change in the angle between AC and AB. So that change in angle is what we call as the angular deformation or shear deformation between AB and AC. So I hope I am making it very clear what do we mean by shear strain rate and why we cannot talk of any shear strain rate if you consider a single material line evolving. So once these basic framework and visualizations or you can say conceptualizations of these ideas are there, the strain rates, what are the longitudinal and shear strain rates, how we can talk about them in case of fluid like continuum, and what do we mean by rotation in a fluid. So once these ideas are there, then we can move ahead and look at the possibility of rigorously, mathematically expressing these in terms of the relevant quantities in a fluid medium, moving fluid medium. Okay, so let us start doing a little bit of analysis for the local deformation and rotation rates. And as I said, we'll restrict our attention to two-dimensional flow domains because to start with, that is the most logical thing to do. Let's restrict to a simple scenario so that we can easily understand and easily perform the mathematical analysis. So as you can see, the figure shows that tiny portion of the material line AB. Implication is that this is an instantaneous small tiny portion of a material line, and to keep matters general, I have shown that it is inclined at some angle theta with respect to the x direction. Since we are talking in two dimensions, so we have let's say two Cartesian coordinates x and y that help us to analyze, and material line portion AB, just to localize the deformation and rotation rates. In the sense of calculus, we take it to be infinitesimal. So the length AB is shown as symbolically delta L, and there are a set of unit vectors t cap and n cap, one aligned along AB, so t cap is aligned along AB and n cap is aligned perpendicular to t cap. So these are the two vectors. You will soon see why I need these two vectors. So if my angle of inclination is theta for AB, then I can simply say that the unit vector t cap has components cos theta and sin theta, and the perpendicular unit vector n cap will of course have the components as minus sin theta and cos theta. So I have just written the components. If you want to write the vector, then you can use the I cap and j cap unit vectors along with these components to express the vector. But this is sufficient. This just we need to consider only the components. And then we write the velocity vector, which is of the fluid particle at A, and symbolically again the components are written U, A, V, A. Now this is the first major step that we take forward from here. Now in the neighborhood of point A, neighborhood means just any amount of displacement in any direction that you may desire from point A. Neighborhood means if you are at point A, then if you displace delta x and delta y from A, then you can express the velocity using Taylor series expansions. Why? Because remember, if you have a continuous function, then knowledge of the function and its derivatives at a particular location will allow you to estimate the value of the same function in the neighborhood. That's what the usage of Taylor series is. Okay, so in 2 dimensions, at a particular instant in time, we are expanding the velocity components u and v. That means these are my two functions u and v as functions of x, y and t. This is the velocity field in 2D. Most general velocity field means it can be dependent on time. So at a given instant, if you fix the time, then it is only going to depend on x and y. So if you expand in a Taylor series, the expressions would look what I have written here. U and V, they will be the Taylor series expansions will look like this. So if I read only one of them, that should be sufficient for you to understand. So U is equal to UA, means U in the neighborhood of A at a point which is displaced from A by an amount delta x and delta y in the y direction and delta x in the x direction. If you displace yourself from point A, then the velocity u will be equal to ua plus the partial derivative of u with respect to x at point A multiplied by delta x, partial u by partial y at A multiplied by delta y, and there will be the series is actually infinite with higher order terms. HOT means higher order terms. So higher order means it will involve higher order derivatives of u with respect to x and y, and the small displacements delta x and delta y will be having higher powers than unity. That means 2, 3, like that. So those are the higher order terms. Now what we do here is that since we are restricting ourselves to a very small, tiny, infinitesimal material line portion, so it means that our delta L is actually in the sense of calculus, it is infinitesimal, or it is very, very small. So if delta L is small, obviously delta X and delta Y are also again going to be very, very small. So for small delta X, delta Y, this expansion that I have written, Taylor series expansion, will be, it's possible to then just neglect the higher order terms and retain only the first order terms, and it will not be a significant loss of information, because delta X and delta Y are infinitesimal in the sense of calculus. So if they are infinitesimal, their higher powers will be very, very tiny and very, very small, so we can simply neglect it and just think of these expansions only up to the first three terms only. That means up to the first order terms. So while I have not written it that way, you need to just restrict your attention only up to the first order terms. Okay, now we can just directly start writing the longitudinal instantaneous strain rate of infinitesimal material line AB, which is instantaneously oriented with an angle theta and is actually anchored at point A. ये जो lower point है, the lower point A is what we call as the anchor point. Okay, so this is the meaning of anchor. So the longitudinal strain rate, instantaneous strain rate, and the instantaneous rotation rate, they can both be directly written now in the manner that I've shown here. Look at the expressions now. Let's focus here on the expressions. So epsilon AB, which I'm calling as the longitudinal instantaneous strain rate of AB, and it's also written as epsilon theta, because after all, what is AB? AB is just an infinitesimal material line. It is characterized by its slope, right? Its angle rather, with respect to the x direction. So whether you write epsilon AB or you simply write epsilon theta, meaning is well conveyed. Okay, so we will prefer the subscript theta because it allows us to remember the orientation of this material line that we are considering. So epsilon AB is equal to the relative velocity of B with respect to A dot product with T cap. What does this give me? It gives me the component of relative velocity of B with respect to A. Which component? With the component which is aligned along AB. After all, the component which is aligned along AB, that will be responsible for change in length of AB, either expansion or contraction. Similarly, the rotation rate, omega AB or omega theta as you can say, this will be defined as the relative velocity of B with respect to A dot product with n cap. Why n cap? Because it's the perpendicular relative velocity component of B with respect to A, which is responsible for rotation of this material line AB. So it's the perpendicular component, and if you divide the perpendicular relative velocity component by the length of the line, it gives you the angular velocity of this line. Remember, two dimensions may, if something is rotating, a line is rotating, then the relative normal component of relative velocity of one end with respect to the other divided by the length gives you the angular velocity of the line. So that fact has been used here. So this completes rather the basic expressions for local deformation and rotation rates in two dimensions. Now we can, so I've already told you that what are VB minus VA dot T and VB minus VA dot N. So I don't need to, the explanation is written here right at the bottom right side of the slide. So this completes what we set out for. The objective was to can we arrive at some mathematical relations for deformation and rotation rates in 2 dimensions. So taking the analysis further, we can use these expressions that we have obtained for the strain rate epsilon theta and rotation rate omega theta, and use the Taylor series expansions to recover the components of the relative velocity ub minus ua and vb minus va. So in the Taylor series, I just have to substitute the displacements delta x and delta y as delta L cos theta and delta L sin theta. Why? Because these are the displacements of the other end of the material line B. So since we need UB minus UA and VB minus VA from the Taylor series, we have to substitute the appropriate displacements delta x and delta y, which correspond to the other end of the infinitesimal material line, that is B. So substituting the delta x and delta y for that point B, and performing the dot product. We know how to take the dot product. I don't need to tell you that at this stage. So just write the vectors using I cap and j cap and then take the dot product. So all that maths is available in the class notes that I will soon be uploading in PDF format. So that detail will be there in those notes. In the lecture video, I am skipping all those details for obvious reasons. So we will get the final expressions in a rather interesting form, and these are omega theta, as you can see, 3-term expression which involves all the 4 partial derivatives: del u del x, del u del y, del v del x, del v del y, and some you can say trigonometric ratio expressions: cos square theta, sin theta, cos theta, and sin square theta. So this is a very interesting looking expression, and it will be discussed further towards the end. Similarly, the strain rate epsilon theta also involves all the 4 partial derivatives and the trigonometric ratios cos theta, sin theta. So these are you can say fundamental, you can regard them as basic fundamental expressions for longitudinal instantaneous strain rates and instantaneous rotation rates of what? An infinitesimal material line which is instantaneously anchored at some point in the 2D flow field. Notice that I have removed the subscript A now from the partial derivatives, because A was just an arbitrary point in the 2-dimensional flow domain. You can consider a timeline in any way, and you can choose any point on the timeline, any point A, and take a neighboring point on the timeline B. So that's why there's no significance of that point anymore. Once all the conceptual framework is you can say established and the maths has also been completed. So finally we need to regard these expressions in this manner only, that we are just talking of strain rates and rotation rates in a 2-dimensional flow field of infinitesimal material line which is anchored at some point. And the importance of the point is that wherever you choose that point to lie, the 4 partial derivatives you need to consider at that point. Okay, and then once you are anchored at some point in the 2D flow field, you can choose the material line, infinitesimal material line, to be at any angle right from 0 to 2 pi. Okay, any angle you can choose. So depending on the angle and the anchor point, you will get the answers for rotation rates and strain rates. So my concluding remarks after all this effort that we have been making in this lecture are just two, and you can just read them off on the right. Both epsilon theta and omega theta depend upon which two factors? Let's focus on the expressions now. The first factor is it depends on the orientation of the infinitesimal material line at some point in the 2D flow domain. So orientation at some point in the 2D flow domain is necessary to talk of these rotation rates, local rotation rates and strain rates. Similarly, longitudinal strain rates, of course, because we have considered a single line. So as mentioned earlier, no talk of any shear strain rate as yet. And the second dependency is on the four important partial derivatives of the velocity components, okay, at, of course, the anchor point. So now you must realize that since you are working in two dimensions, so in two dimensions you have got only two components u and v, and each of them will have two spatial derivatives, derivatives, del u del x and del u del y, similarly del v del x, del v del y. When we will be extending these ideas into 3D, you can very well imagine there will be in all three components of velocity that should play a role, and their derivatives will also be 3 for each, so making it a total of 9 spatial derivatives. So I am just hinting at some things to come in future. Now the second or the last thing that I need to point out from these expressions, notice the dependency on theta, cos square theta, sin square theta, sin theta cos theta. So they always occur as a quadratic term, cos square theta, sin square theta, or sin theta cos theta. Now once you observe this, you all are knowing basic trigonometry. From basic trigonometry you can always argue that cos square theta can be written as in terms of the double angle, 1 plus cos 2 theta by 2. Similarly, sin square theta can also be written in terms of the double angle, 1 minus cos 2 theta by 2. And sin theta cos theta can also be written in terms of the double angle, single sine term, that is sin 2 theta by 2. So once you can write all these trigonometric ratios and their combinations in terms of single trigonometric ratio sine or cos in terms of the double angle 2 theta, it is very easily to say or state that the dependency on theta is periodic. Why periodic? Because ultimately you can express it as a single combination of single sine or cosine, but not of theta, a function of 2 theta, right? So that's why we are saying that the dependency on theta is periodic with a period, how much? Pi, because the sine 2 theta or cos theta terms are having period equal to pi and not 2 pi. So you can verify this yourself. I have already given you the hint. So what does it mean from the point of view of you can say periodicity? What is the meaning? So if I, for example, the figure shows if I consider a material line AB at some angle theta, and I also consider a material line AC which is having an angle theta plus pi. So it is basically having an angle which is at 180 degrees from the original material line AB. So the effective angle, total angle from the x direction is theta plus pi. So once you consider two material lines like this, then since the expressions omega theta and epsilon theta indicate that it is a periodic function of theta having a pi, we can simply conclude that the strain rates for the two material lines AB and AC and rotation rates would be same. Okay, so this is where I will like to conclude this second lecture of mine, and we'll pick up in the third lecture by starting, discussing more on these results that we have got. And of course, one shear strain rate which we have not yet evolved the expression for that. We will evolve some expression for the shear strain rate by considering two material lines, and then we will see some very interesting properties associated with these local deformation and rotation rates. So that will be taken up in the third lecture. So this brings to the end of my second lecture, and as I said, detailed notes of the derivations and things like that you will be getting in PDF format. I will soon be uploading, but I'll upload it probably after another lecture or so. So once lecture 3 is over, then you will see that the PDF notes are also uploaded in the Google Class room. Thank you very much.